Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. So let us continue with our chapter number 1. Okay, with the topic of again in generation of three-phase voltage, and so we have seen how the Y system works. All right, so including the Y system over here connected with the fourth wire, neutral wire. So this is the load system, another Y connection, and so it is also referred as star configuration, right? Instead of Y, so we have also star configuration. Okay? So the outgoing lines are called line of phase conductor. So this is the line over here from the voltage supplied to the load. Okay, so all current flow is actually the line. It is called line of phase conductor. All right. So line voltage or voltage between lines either at the generator or at the load. So this is the voltage. The line voltage is the line number 1 to line number 2 or to line number 3. All right. So we have the second system, namely the star delta system. So we can also alternatively separately connect the generator coils and the loads in the star or delta formation before connecting them together to form a YY or star star, Y delta or star delta, delta Y, or a delta delta system. So this means altogether we have 4 possibilities configuration. Okay, basically we have star and delta only. Okay, so this is the second possible configuration, namely star delta connection. Here, these two. All right. So this is what we have seen earlier, the 3-wire Y to Y system, and here is the Y delta system. All right. So pen. So note, so phase voltage are voltage across phases. For a Y load, phases are from line to neutral. From line to neutral. So this is called phase, right? Okay, especially for V phase. Okay, so particularly for delta configuration, and then for load, or for the delta load, okay, the 3 phases are from line to line here between these two. All right, so this is called V phase. Okay, so similarly from this line to the bottom line, so we have another V, so we have another V phase. Okay, all right, that's for star and delta. Okay. So what about delta delta, okay, and delta Y system? Okay, so this is delta to delta, okay, and this is delta to Y system. So this is basically similar to star delta. All right. So but this one is a new configuration. The combination between delta and delta. So some of the nodes, so phase voltage are voltage across phases. For Y load, this is similar. So for a Y load, phases are from line to neutral. For Y again, so from this line to neutral, this point, this is neutral again. I repeat, this is the phase. All right. For another line, the second line to this point or neutral point, this is another phase. Similarly, for the third line to this point is the third phase, especially the phase voltage. Okay, for data load, the phases are from line to line. Simply this between these two, all right, these two, and these two. All right, this is the phase. Okay. So line current are currents in line conductor here. All right. This current here. Okay. Here, traveling okay to the right side of the system, the load, for example. Similarly, here we have another current flow. All right, throughout the line. Okay, so this is all I. Okay, this is I. This is another I. Okay, so this is how current flow inside star or star configuration. Right, so similarly here, so this is I direction, here is another I direction, etc. etc. Okay. So for a well-connected load, the line current is also the phase current. So this is very special for star connection. So let's say we remove load first. Okay, all the boxes here. So it simply remove. So we will see this simple Y or star formation. So we can say that this current flow over here, for example, so the I line is actually equal to IP. So we will see later the relationship between line and phase element, namely current. So according to delta and star configuration. All right. Okay, this is what I mean just now. So star and delta connection, star and delta connection. So what are their relationship between element of current and voltage? So for star, IL equal to I phase. All right, here this is also known as IL. Okay, and then VL, this is equal to square root 3V VP. So VL, for example, from this line, line number 1 to line number 2, okay, this is equal to, all right, square root 3V VP. Okay, this point, this point number 1 to this point N. All right, so this means line voltage VL of point 1 or node 1 down to node 2, this is equal to square root 3 Vp of node 1, so down to node N. All right. So this is the relationship between V line and V phase. What about delta connection? Right. So delta connection is what I told you earlier. So R line, this sorry, the one I told you earlier was about delta connection, so star connection. But when you come to delta connection, so it is totally different. So our relationship is something like this. So this is square root 3, this is square root 3. All right, for I, L and IP. So this means IP, IL, this is equal to square root 3 I3. Okay, but when we talk about VL with these two, this is actually equal to VP over here. All right. So between these two, the potential between these two nodes or these 2 points across this phase, so this is actually equal to V line. Okay, VL equal to V phase. Yeah. All right. So data tries to equal the voltage. So applications used in equal voltage situation like motors, etc. etc. Okay. So application is mostly in machine motors. All right. So for star, so some additional note over here. Always try to equal the current. So where IL equal to IP. So we get two voltage levels can connect a single phase load. Two voltage level means this is single phase, okay, and then this is three phase. All right. So we have two voltage level. Okay, phase single phase as well as three phase. So can connect a single phase load. So phase sequence is the order in which the voltage in the individual phases peak. Okay, so peak here at this point, at this point, at this point. For every individual phase, right? For Rn, Yn, and also Bn. So for a three-phase system, there are only two possible phase sequences, either RYB or RBY. Okay, can be either RYB. Okay, again. Okay, so this is we call positive sequence, right? So this, meanwhile, for the second sequence, we have R, B, and Y, the so-called negative sequence. Okay, only these two possible sequence. Okay, so corresponding to the two possible direction of alternator rotation. This means for the alternator, for example, this is the design of what do you call it, generator or alternator. So we do have the CCW direction. We have the CW direction. Okay, so the angular velocity W, for example, this is for the symbol for velocity, angular velocity, right? So it may rotate according to CCW, the counterclockwise direction, or CW direction. So this sequence, two sequence, correspond to this phenomenon. Okay, two possible direction, right? So this is how we can measure the waveform, the sinusoidal waveform. Okay, the fundamental sinusoidal waveform, which is separated by 120 degree apart. Okay, from one signal to another. All right, according to its respective phase, of course, right? R, Y, and B. This one. So this is what this is more detailed. So we have the Rn over here. This is phase Y, and this is phase B. Similarly, similar to what I have shown over here. All right. So 120 degree for each angle. All right. So negative sequence, yes, R, B, and Y. Okay. Again, for positive sequence, so this is how it looks like in terms of waveform. So we have R, Y, and B sequence, and the phasor diagram R, Y, and B. Okay. And then for negative sequence, so R still same. So we have what you call maintain the position of R, which is become the reference over here. So if we assume the horizontal line is the always become the reference. So this horizontal line with 0 degree theta, all right, mean the position here, 0 degree. So this is always become your reference. So we start with Rn as your reference, followed by Bn as well as Yn. So yes, the position of the the rotation, the direction direction of rotation of your motor is either CW, or this is actually CCW, because from R to B, now we have R to Y. It's supposed to be like something like here. Okay, for this one. Okay, actually R to Y. For this one, positive sequence from R to B, but this one R to Y. But once we rearrange the phasor diagram, it looks this way. Okay, upper way. Okay, but still from R to Y. Okay, this means opposite direction compared to the first sequence, R to B. Okay. Okay, example 1.1, determine the phase sequence of the set of voltages. So we have the first phase both voltage phase, VRN, V second phase, okay, so third voltage phase voltage, okay. So we have the value of V 200, the maximum, okay, the peak of the value. So we have is angle, all right, the phase angle, all right. And then solution number one, so determine the phase sequence. This phase sequence is just like what we have done earlier, okay, in the previous slide. Okay, so we start with this what do you call it, the axis. So this is the y-axis, for example. This is x-axis and y-axis, horizontal and vertical axis. So this will become again your reference. So the voltages can be expressed in phasor form as 210, 200 minus 230, 200 minus 1, 110. So you just remove the cos over here. All right. So we just have the magnitude. This one, the value, magnitude, as well as the angle. Okay. So to stay 200 minus 250, 230, 200, 100 minus 110. So how to draw the phasor diagram? So this is how it looks like. Okay, this is your angle degree over here. Your reference, I will start from this position. Okay, your reference. So the VRN is actually 10 degree above your reference. So again, this is 0 degree. This is your reference, 0 degree. So back to VRN value, it is 10 degrees shifted upward. Okay, this is 10 degree. Okay, shifted upward. Okay, so 10 degrees is not much compared to the straight line or this horizontal line. So you can see it slightly move upward. So yes, with the symbol of error, so showing the direction of the phasor, and then this bold line. Okay, the bold arrow is actually representing the magnitude of 200. Okay, so the longer the arrow means the higher the value. All right, so just assume you have this axis, all right, and then you have 200. Now you have 250. Oh, I should write in the same diagram. So let's say you have 250 volt for your VRN. So how to draw, how to represent? So you should now VRN prime to show this is a new VRN compared to the previous or the old VRN. So now we have a longer 30. Let's say we put 30 over here. All right, just to separate between the old VRN. Okay, so we have 30 degrees shifted upward with longer arrow. Okay, so longer arrow means this is 250 volt. All right, then the angle is 30, is wider. We have 30 degree, is wider compared to only 10 over here. So the old VRN. So now we have VRN prime. This is 250, and then look at again, look at the arrow. So we have longer. So this is 200 because this is only 200. The shorter one means the lower value, 200. Okay, so we have done VRN. So we move on to second phase, which is VYN. So let me change to yellow color. So YV, where is it? Where is it? Where is it? So the yellow color over here. Okay, sorry. So this is VYN. Again, same magnitude, but this time we have minus 230. So minus 230 from your reference over here. So this is minus 90. So this is minus 180. So we have minus 50 degree more to equal to 230. That means we have somewhere here the minus 230. All right. So before I forget, so the minus and plus, positive and negative, so indicates the position of the arrow, the phaser. So minus mean upward here. This is, sorry, this is plus degree theta. So from here, again, your reference, this is always 0 degree. So downwards mean negative theta. If you go downward, this means, so this is negative theta. So if you go upward, okay, this is positive theta. Okay, so just like the first example again, this is positive 10. Positive 10 means it is going upward, or CCW. Okay, VYN, the second phase is negative 230. So negative 230 means it is going down here, the CW direction. Okay, so up to this position. So this is your VYN, the second phase. The second phase, sorry. And then the third one is BVN. Again, you still have the 200 volt for your magnitude, but this time we have minus 110. So again, from your reference, so move down because it is a negative sign. So this is minus 90, and we have slightly 20 degree more before you reach the position of the question over here. Okay, so 20 degree more from 90 degree line over here. So this is 20 negative, or just simply 20. This is 90. Okay, so you plus 20 and 90, you got minus 110. So that means this is actually minus 110 degree. Okay. So notice that VRN leads VBN by 120 degree, VBN in turn leads VYN by 120. Hence, we have an RBY sequence. So after you plot out everything over here, so you will come to conclusion that VRN, okay, is actually ahead of VBN, okay, by 120 degree. All right. If you recalculate the position and the angle, so you will see that VRN is actually ahead of BN by 120. Similarly, if you recalculate the position of the angle of the BN compared to YN, so BBN is ahead of BYN by, again, another 120 degree. And the drawing itself show, or the position itself of each individual phase shows that the sequence of the phaser is actually R, B, and Y. All right, so R, B, and Y sequence. So superiority of three-phase over single-phase electricity. Why three-phase is more important, is more crucial, or is more superior compared to single-phase electricity? So three-phase transmission line require much less conductor material. Why? Because the phaser sum of currents in all the phases is zero, means it's stable. So when we come to the total current of the three-phase line, right? Because yes, due to the thanks to the balance system of your three-phase transmission line, so there is substantial saving by eliminating the return conductor, replacing it by a single neutral conductor of comparatively small size. So out of three-phase, for example, so one return line, which is called neutral line, is sufficient, is enough to represent all three line, 1, 2 over here, and 3 over here. This is sufficient to represent this line, and enough with one return line, so-called a neutral line. Okay, So all three-phase machine give higher output than a single machine, of course, due to the better power supply of the three-phase, so more better performance of the system. A machine, for example, okay, because it is operated at three-phase voltage. So the sum of powers in three-phase system is constant compared the single-phase system. Okay, this is one we come to again to the sum of P in three-phase, for example. So this is more constant, okay, or more stable. So the three-phase supply can generate a rotating field, all right? Okay. Three-phase induction motor are self-starting, so this is some of the advantage of the induction motor. So the three-phase system can to supply domestic and industrial commercial power because it can be downgrade to 240, all right, for single phase, and of course up to 415 for three phase at the industrial or commercial utilities or equipment they are using. So the voltage regulation in three phase is much better than that in single phase surplus due to the what they call it, stability of the system. So again, the comparison of power output, single phase, two phase, and three phase. So the single phase power output is not constant, and the average power is half than its maximum power. So you have two problems over here. It's not constant. The power output is not constant. Okay, and then the average power is only maximum. Is half than 50% of maximum than its maximum power. The maximum output power. So if you come to the average power, so it's only give half than its maximum power. So meaning much loss in this particular single phase system. So what about the second phase power output? So yes, it is constant at every instant, and the average power is equal to maximum power of the maximum power of the output. So we have the average over here. Okay, this is actually equal to the P max of the system. All right. So what about the three phase? So constant at every instant, then average power is actually 1.5 times greater than the maximum power. So this is the advantage of the three-phase system. We have the average power, which is 1.5 greater than the maximum power. All right, so more reliable system when it come to power. So some of the YouTube I will include the link of or the source of this YouTube in your classroom folder, Google Classroom. All right.